Hi. We are dealing with the combinational circuit synthesis. In this chapter, we have examined the synthesis concept in general for combination circuits, and then we introduce a method which finds the minimal function, and that method was Ch4-3-1 method. Now we will be examining an alternative method to Ch4-3-1 method in order to find the minimal functions, whether it is sum of products form or product of sum form. So we will be examining this method now. That is the frame that we're going to examine. So the first video is related with the Kaurgaugh map representation of the Boolean function. The second one, the terminology that we are going to use for Kaurgaugh maps. And in this third frame, we will be examining the Kaurgaugh map method. So within this frame, there's going to be three videos. The first one is related with this one, and it is a small video. So let me go in there. Present. Here you are. Representation of a Boolean function. As you know, there are different representations. One of them, you can write the true min terms of a function with a sum sign, or you can write 0 points of the function in decimal and put a multiplication sign in front of it. These are just the lines. Or you can use the truth table as you see it here. For a 3-variable function, we've got 8 lines, rows, and 4 columns. These first 3 columns related with the independent variables. The second column is the representing the value set, function value set. Now we are saying we can represent this through truth table in a different way. This is called the Kaurgaugh map. Kaurgaugh map has got this 3-variable. Kaurgaugh map has got 2 rows and 4 columns. These 4 columns represent x1 and x2 variables values. There is something special for these columns. If you look for the columns next to each other, for example this one 0, 0 and 0, 1 column, only one variable is changing from this column to this column. That variable is x2, isn't it? x2 variable value for this column is 0, while for this column it is just 1. So, but x1 value is not changing. So in neighbor columns, only one variable is changing. If you compare these two, for example, x1 is changing, x2 is not changing. If you compare those 3 on third and fourth columns, x2 is changing, x1 is not changing. So that is the property of Kaurgaugh map. This coding should be as it is seen here. For the row case, so this is just 2 rows we've got. So since we've got 4 columns and 2 rows, the total number of cells that we have in this Kaurgaugh map is just 8. So 8 is also the number of rows in the truth table of this 3-variable function. So each row has a corresponding cell in this Kaurgaugh map. So the values of the function we are going to write inside the cells. So in which cells functions which value we are going to put in is easy to answer to that question, because you see this cell, the first cell here is in the first row and first column. So if you look at the variable values for this first column, first row is 0, 0, 0. So that is this one, isn't it? This first row here. So function value is 0. So this cell corresponds this first row here. In decimal it is 0 column. Function value is 0. We don't write anything if it is 0 value. If the function value is 1, we can write this one inside the cell. So let's look at this one, 0, 1, 0. That is this row, 0, 1, 0. this cell, function value for this row is equal to 1, so we put that 1 in. If you continue like that, you can transfer all these function values to this. As you see here, we've got 4 ones in it, so we've got 4 ones in this Kaurgaugh map. And the empty cells means function value is 0 for those cells. So what is special here in this Kaurgaugh map is this. The neighbor cells, for example, 2 and 6, represent the variable values, only one of them is changing. What I mean is this. So if I compare these two cells now, x1 value is changing, x2 value is not changing, x3 value is not changing for 2 and 6 cells. So what is the property of these 2 and 6 cells is that they are the neighbor cells, isn't it? 2 and 6 are neighbor cells. What I mean by saying neighbor cells, one of the line of these cells are common, isn't it? So I call it neighbor. 0 is neighbor to 1, but 0 is not neighbor to 6, but 4 is neighbor to 6. For example, 1 is neighbor to 6. Sorry, this 7 cell is neighbor to 6, 3 cell is neighbor to 2 cells. So you can see the cell neighbor cells, and we know that neighbor cells corresponding rows variable value is changing only one for variable, not for the other variables. One thing that we've got to mention here, although this 0 and 4 cells here does not seem the neighbor cells because there is no common line between those two. But if you consider this line and this line are connected together at the back, then it is going to be a cylinder. So if you consider the surface of this cylinder, this 4 and 0 becomes neighbor cells. This 1 and 5 also becomes neighbor cells. So you're going to consider the cylinder's surface. You cannot see the cylinder here because this is two-dimensional. Cylinder is a three-dimensional figure, isn't it? But you're going to consider this while you are thinking about the neighbor cells. The second one here is a 4-variable Kaurgaugh map. For the 4-variable truth table, we've got 16 lines and 5 columns. The first 4 columns related with the independent variable values, and f dependent value is in the last column. So if you look at this Kaurgaugh map, this part, the top 2 rows and last 2 rows are repetition. So this 2 rows, if you x3 value is equal to 0, the last 2 rows x3 value has got 1. Okay, so this coding here, the row coding, is in the same order as the column order here. So 3-variable column orders are the same whether it is 3-variable Kaurgaugh map or the 4-variable Kaurgaugh map. So in the 4-variable Kaurgaugh map, we've got 4 rows. For these rows, coding is the same order as we have the column order, isn't it? 0, 0, 0, 1, 1, 1, 1, 0. It's not like that 0, 1, 1, 0 here. This coding order is important. I will explain why it is important. It is related with the neighbor cells business once again. In this map again, these if 2 cells are neighbors, that means one of the lines of these cells are common. 4, 12 is neighbor, but 4 and 8 cells are not neighbor. Before that, I should have said that each cell here is each cells in that 4-variable Kaurgaugh map represent a row here. This representation relation is directly, you can see it. For example, that 6 here, 0, 1, 1, 0 row, isn't it? So 0, 1, 1, 0 is this, isn't it? 0, 1, 1, 0. Here you are, 6 cells. So the row directly corresponds to that cell. Now the neighbor cells, as I said, if they're one line common between two cells, we call them neighbor cells. Property of the neighbor cells is this: independent variables, only one of the variable value is changing, while the other variables values are the same for the neighbor cells. This property is always true for neighbor cells. Similarly, for this one, we said we are going to consider this line and this line are connected at the back, so it becomes a cylinder surface. Now in here we are going to consider this cylinder has got base, upper base and lower base. If you consider those two bases are connected together, so it will be a Tor type thing. So if you consider this Tor type figure surface, this surface is going to tell me 4 and 6, they are neighbor cells. Why is that? Because the Tor upper base and the lower base come together, these two lines becomes common between these two cells. So I can outline these neighbor cells now. 0 and 8 are neighbor cells, 1, 9 neighbor cell, 3, 11 neighbor cells, 2 and 10 are the neighbor cells. Similarly, 2 and 1, if you consider the base cylinder bases connection, 0 and 2 neighbor, 4 and 6 neighbor, 12 and 14 neighbor, 8 and 10 neighbor cells. Of course, inside this 7, 15 is neighbor. For example, 14 and 5 is not neighbor. 5 and 9 is not neighbor. So the property of the neighbor cells, as I said before, is true for this 4-variable Kaurgaugh map as well. If two cells are neighbor, that means one of the variable value is changing while the other variable values is not changing. Then these are the neighbor cells. So we are saying now this 4-variable Kaurgaugh map, in a 4-variable Kaurgaugh map, I can represent all the 4-variable functions. How I am going to represent it? Each cell here represent a row here is if the function value is 1. Inside the corresponding cell I am going to write 1. If the function value is 0 for a row, the corresponding cell I leave is empty. When it is empty, it means 0. So if we count now the number of ones here, 1, 1, 1, 3, 4, 5, 6 ones we've got in this function. So you see that 4 ones here and then 6. So you can check these positions, these cells, has got the value 1, the corresponding row function values are 1 as well. So how we are going to use the Kaurgaugh map is the next step. So that's the end of this video.